Hello, this is Pat Hindle, editor at MicroWave Journal. It's my pleasure to welcome you to today's webinar on optimizing peak to average power ratio for wireless systems, presented by Mark Elo, U.S. General Manager for Tabor Electronics USA, and Walt Strickler, Vice President and General Manager of Boonton Electronics. Before we begin the presentation, let me cover a few items about the On24 webinar platform. In the center of the screen, you will see a window containing the presentation. You may enlarge this to full screen to get a better view of the slides. The window on your screen labeled Resource List contains a copy of the presentation, which you can download at any time. The webinar is being recorded and is available for replay, so that you can watch it again and recommend it to colleagues who weren't able to join us today. You will find a link to the recording in the events section of the MicroWave Journal website. If you have technical problems, please click on the yellow box with the question mark at the bottom of your screen. It will take you to a helpful user's guide. If you'd like to ask a question, just type it into the Q&A box on your screen, and we'll address the questions at the end of the session. Please note that we have added a COVID-19 widget at the bottom of your screen, which links directly to the COVID-19 Solidarity Response Fund for the WHO. On24 will make donations for visiting the site. The signals used in today's most advanced communication technologies can employ various modulation and multiplexing techniques to optimize different parameters, such as spectral efficiency, susceptibility to interference, and data rate. Correspondingly, these signals can have widely varying peak-to-average power ratios. If the peak-to-average power ratio is too high, it can lead to spectral spreading or regrowth. However, lowering the power can lead to less efficient operation of critical components like power amplifiers. This webinar will explain how to use advanced arbitrary waveform generators to create signals with varying peak-to-average power ratios and how to simplify and cost-effectively measure peak-to-average power ratio using RF peak power sensors throughout the RF transmission chain to make trade-offs for optimal system performance. I'd like to introduce today's presenters. Walt Strickler is Vice President and General Manager of Boonton Electronics, a wholly owned subsidiary of Wireless Telecom Group. He is a seasoned veteran of the test and measurement industry with previous experience at Anritsu, Gigatronics, Bird Technologies, and Keithley Instruments. Prior to that, Walt worked at the NASA Glenn Research Center focused on microwave communication. Walt has a BSEE and MBA. Our other speaker is Mark Elo, who is a U.S. General Manager for Tabor Electronics USA. He began his career as a design engineer in Hewlett-Packard's microwave division and has since held various senior positions at Agilent Technologies, Anritsu, Gigatronics, Keithley Electronics, and R&D, marketing, and business development. Mr. Elo has more than 30 years of test and measurement experience in the microwave instrumentation, specializing in product definition and product realization of RF and microwave frequency synthesis and analysis platforms. This webinar is sponsored by Boonton Electronics, a wholly owned subsidiary of the Wireless Telecom Group, and Tabor Electronics USA. Tabor Electronics has become a world-renowned leader in the signal source market. The company's product portfolio includes signal amplifiers, pulse, function, and arbitrary waveform generators, waveform creation software, and more in various platforms, interfaces, and frequency ranges. Technologically advanced, featuring the highest levels of performance, reliability, and most of all, price competitiveness, they are sought after in a diverse array of applications. Throughout the years, Tabor has produced its own branded products and was an original equipment manufacturer for leading brands in the industry. Setting the highest standards in accuracy and ease of use, Boonton Electronics is recognized as a leader in high-performance test instrumentation and sensors. They are a manufacturer of test equipment dedicated to measuring the power of RF and microwave systems used in both military and commercial sectors. The company also manufactures impedance measuring instruments, RF voltmeters, and audio analyzers. Boonton's products are currently used to test terrestrial and satellite communication, radar, telemetry, electronic warfare, electronic countermeasures, and an expanding number of wireless communication products. So at this point, I will hand the presentation over to Mark and Walt.
Thanks. Both Walt and I welcome you to the seminar. We'll be focusing on multi-carrier systems, namely orthogonal frequency division multiplex, as that's the most ubiquitous modulation scheme used in modern communication systems, and its evolution really drives the way you design your circuits or your components and how we design our signal generators and power meters. So, what are we going to cover today? Well, I'm going to kick off the first part by taking a close look at the signal. We'll start with a couple of tones and look how they interact or how they superimpose with each other as vectors, and then we'll expand that out to multiple tones, and then we'll quickly learn that the traditional measurements such as average power need to be complemented by peak envelope power, and ultimately when modulation is added we need to take a statistical approach and plot out power behavior over time or a time interval using a complementary cumulative distribution function, or more easily said as a CCDF. We'll then move on to different signal generation techniques, as the new standard's goal is always to increase throughput, so more subcarriers are always needed when you do that in an OFDM system. Then we'll move on to the second part, and Walt's going to talk about how we apply our signal knowledge to amplifiers and how we optimize their performance versus cost versus size versus complexity. He'll focus on some measurement techniques that we briefly covered in part 1, such as the average, peak, and CCDF. But then he'll summarize everything that we've learned in both parts 1 and parts 2 with a demonstration, and then we'll wrap up the seminar and open the floor up for questions. To help us understand signal generation, I'm using two types of instrument. The first is the new Proteus P9082 arbitrary waveform generator. This allows us to generate both tones and modulated signals with bandwidths up to 4.5 GHz and a frequency range of 9 GHz. It comes in multiple form factors, has an optional RF digitizer, and an onboard user programmable FPGA for when you want to perform highly integrated closed-loop measurements. For higher dynamic range, multi-tone measurements, the Lucid LS1281 family of signal generators can be configured to have up to 16 analog carriers per unit, and again it's available in multiple form factors. All the signals I used in this presentation today were generated using MATLAB. I used release 2019B, and I also used a spectrum analyzer from Anritsu and an oscilloscope from LaCroix to visualize the signals in both the frequency and time domains. Let's start by generating two tones. In this example, I've used a two-channel Proteus AWG to generate the two tones around a gigahertz center frequency, and they're separated by 80 megahertz. I got the frequency domain display here from the spectrum analyzer, and here I've got the time domain plot from the oscilloscope. Now, in the frequency domain, what this plot does not show is how these two frequencies, or vectors, as they both have an amplitude and phase component, constructively and destructively sum, producing a variation in the amplitude due to the superposition of the two signals. I can easily visualize this on the scope though, and looking at the two signals. So I've got channel 1 here as the red signal and channel 2 as the yellow signal, and I'm using the math function to sum these two vectors here, and you can see when the phases are aligned, or they have the vectors are aligned, we get a peak amplitude, and when the vectors are 180 degrees out of phase, we get a minimum amplitude. Now, when I only have two tones, it's quite easy to put two tones in and use two channels on an oscilloscope and visualize how multiple tones interact with each other. However, in a modern communication system, using multiple tones is a much better way of creating a representative signal. In this example, I've generated 10 tones in MATLAB. As you can see on the left-hand side with these blue plots, I have the upper plot here with a constant phase distribution optimized for the worst case superposition of the waveforms, and on the lower plot I've distributed the phase relationship of each carrier randomly. Then using the spectrum analyzer and using the oscilloscope, I've measured each one in the frequency and time domains. And you can see between the two time domain plots here from simulation and the oscilloscope, we've got a good correlation. So we know we've got an accurate representation of the signal that we've created. Now, if I look at the two spectrum plots, I can see that they look almost identical. But here in the time domain, you can really see the differences between the peak and average voltages. So on the upper plot here with the constant phase distribution, we have a very we have a big ratio between the peak voltage and say the average voltage that we would measure across a number of voltage points here. For the random phase distribution, you can see the peak to average voltage is much smaller. You can kind of see that in the spectrum analyzer plot. If we look at the carrier amplitude here, it's a couple of dBs higher than the carrier amplitude in this upper plot, which tells us that the average power here is going to be a little higher. So our peak to average ratio is going to be a smaller number than the peak to average ratio here. Clearly, when we just use average power, which is typically what a spectrum analyzer measures and an average power meter measures, we now know that it doesn't really tell us the whole story. We really need to understand what our peak power is and how that relates to our average power. And then as we go through the presentation, you'll also see how the CCDF function, which I talked about earlier, how that tells us a little more information over time and really gives us the rate of occurrence of a specific peak to average power ratio. So far, all our carriers have not been modulated, but we do have to transmit information, so we do need a modulation scheme. The IQ modulation process is the most common way of sending digital information. It's essentially an amplitude and phase modulator. The carrier frequency here is fed to one mixer, and we call that the in-phase component, and then there's a 90-degree shift and we send it to the other mixer here, and we call that the quadrature component. And by mixing the information that we wish to transmit with the in-phase and quadrature, we'll get a summation of these signals, and it will create a vector of a specific amplitude and a specific phase. Now, and we usually look at these on vector diagrams. So if our two inputs here have a negative voltage, we'll get a superposition of a sine wave that's in phase and that is quadrature out of phase, and that will give us this vector here at a 45-degree angle, and we'll say that will represent our symbol of 0, 0. If we set both of these to positive, then the vector will flip over to this side of the vector diagram, and we'll have this phase, and we'll say that gives us a symbol representation of 1, 1. And then if we make one negative and one positive, or vice versa, we get the symbols or the vectors rotating around the diagram this way or this way or this way or back and forth like that to represent the symbols 1, 0, 0, 1. Now, it's that process of when the symbols move, or we move the vectors, that can cause our peak to average ratio issues. Here's a real-life plot of how symbols transition from one vector state to another vector state, and we know that the outer circle is higher voltage, and so when we swing from here to here, we can see we get some peaks, and then within the middle here, we can see we get some on and off states due to switching, due to the vector passing through 0, and in essence, we get this like peak to average voltage with the QPSK modulation and with the higher orders. QPSK is 4 QAM and like 16 QAM, 64 QAM, 128 QAM, all create different types of peak to average ratio. So it's how do we manage these transitions? So sometimes you don't go through 0, you can offset it. or you can add filtering, which kind of slows down your data rate. So it's where do we put the compromise? Do we have a slower data rate? Do we not go through zero? Or do we design our amplifiers and make sure our DACs have enough headroom to cope with the higher peak to average ratio of these modulation schemes? So we just looked at modulating a single carrier. So what happens if we apply modulation to multiple tones? I think it's important to have a look at OFDM, because this is built on the principle of, instead of transmitting a large amount of information at high speed on a single carrier, why not transmit a small amount of information slowly on multiple carriers? It's essentially a frequency division multiplex system. However, because the carriers are orthogonally spaced, a guard band between each carrier is not required. So the carriers, or what we call the subcarriers, can be very close together. It works on the principle that frequency domain representation of a pulse of energy is a sin x over x function, or sinc function. The trick then is to set the frequency of each carrier so that the individual peaks of the subcarriers all line up with the nulls of all the other subcarriers. Hence the carriers then become orthogonally distributed in the frequency domain. In our previous QPSK example, we fed a stream of serial symbols to our IQ modulator. What we do here is to convert the serial stream to a parallel stream by utilizing an inverse FFT function. This effectively slows down our symbol rate per carrier, but multiple simultaneous carriers give us an effective high-speed symbol rate. This significantly reduces the effect of multipath, and by changing the modulation type on each carrier, it can also help correct for signal-to-noise issues in the channel. In our example here, we're still using QPSK, but we have now the 8 QPSK modulated subcarriers orthogonally spaced over 1 over the symbol rate. The bandwidth of our signal then is simply the subcarrier spacing multiplied by the number of subcarriers, and then you're going to see some effects in peak to average ratio changes as well, because an OFDM system changes its modulation based on the carrier to noise of the channel as well. So if the carrier to noise is poor, we're going to get, we'll probably use BPSK modulation or QPSK modulation, i.e. just move the phase. If the carrier to noise is good in the system, then, or signal to noise, then we'll decide that we want to use something with more amplitude components like 16 QAM, 64 QAM, you know, any of the orders of QAM that helps us more symbols through and a better data transfer rate. On this slide we have 3 MATLAB simulations: 16-tone Rubin phase distribution, QPSK modulated carrier, and 16 subcarriers, OFDM, so they're orthogonally spaced with QPS modulation. So the first 16 tones is a Rubin phase distribution, and this is optimized to give us a minimal peak to average ratio. Note though, as with the other multi-tone signals I showed earlier, this CCDF curve has a sharp knee as the spread of peak to average ratio is more controlled. In the center we have the QPSK modulation on a single carrier, as the peak to average ratio is effectively the amount of occurrences a vector has at a certain amplitude. The roll off of the curve is more pronounced and the peak to average ratio has significantly increased. Finally, when we modulate 16 orthogonal tones, we see that the shape follows that of the QPSK modulation type. And Walt's going to cover more details later about this, but for now it's important to see the difference between multi-tone, a single carrier, and multi-carrier modulation schemes in terms of power behavior. I think it's important to take some time and look at the autonomy of an OFDM signal, because it's more than just a number of orthogonally spaced subcarriers with modulation. In this MATLAB simulation from the communications toolbox, I've created 16 subcarriers, and they're spaced orthogonally at 1 megahertz, and the modulation I've got is defined here, and it's for QAM or QPSK, and it's actually modulated onto 5 carriers here in the center. And then the other carriers within are 16 megahertz of bandwidth. are what are called null carriers or the guard band carriers. So we only have modulation in this part. And you can see this on the spectrum analyzer. So once I've loaded this signal into the arbitrary waveform generator and playing it out here, you can see that it's quite representative of what we built in the communications toolbox. So we've got our modulated carriers here, 1 megahertz space. This is a zoom in here, and then you can see the unmodulated guard band or null carriers here, and we can quite easily measure that there's a 1 megahertz difference between these two modulated subcarriers. The other thing that I've not included in this simulation and play out, I have not included any of the pilot carriers, so sometimes you'll see pilot carriers sticking out of the modulation. Also, because I've used a digital process to modulate the carriers up to the carrier frequency, you don't see any effects of carrier feed through on the spectrum display here, and I'm going to talk about that a little later on when I talk about the architecture of new instrumentation and also the architecture of RF modems. So now we understand the autonomy of an OFDM signal. Here's a couple of real-life OFDM signals that we're going to use as part of this presentation. On the left here, I've generated an 802.11ax signal, and on the right, an LTE signal, and I'm displaying them both on the spectrum analyzer. While in most cases the carrier spacing is fixed, there are multiple bandwidth options, and the bandwidth depends on local spectrum availability versus the data throughput requirement. More data throughput requires more bandwidth, and as our bandwidth is related to carrier spacing, which is fixed, more OFDM symbol throughput will always equate to more carriers. And Walt's going to discuss more how the effect of adding more carriers will affect the peak to average ratio and ultimately the CCDF curve in the coming slides. But for now, let's look at two simulated 802.11ax bandwidth. So we've got 40 megahertz and 160 megahertz on the left and the right here. So in MATLAB, I generated them, I downloaded them into the Proteus AWG, and Walt's made some measurements with the Boonton power meter. The key is to compare the difference in CCDF and understand what causes the difference. The simulation versus measurement correlates pretty well. And note the difference in the two sets of curves though for the number of carriers. Wider bandwidth means more carriers. And you see the area under the curves is increased as the curve or the plot has actually moved to the left as we increase the carriers, and that's what Walt's going to talk about in the amplifier and measurement section. So far we've learned the difference in power behavior between multitone signals, modulated signal carriers, and modulated orthogonal frequency multiplex carriers. And for most of this presentation, we've generated all our signals using a direct to microwave arbitrary waveform generator, which is this thing here at the center of the screen. It's the Proteus P9082, has 4.5 gigahertz of bandwidth and a frequency range of 9 gigahertz. It's built on high-speed DAC technology, and the signal frequency is really determined by the sample rate of the DAC, and then you get higher frequency operation by using multiple Nyquist zones. This type of technology enables wide bandwidths, but sometimes at the expense of amplitude range. However, with multiple launches of Wi-Fi 6E chipsets and ultra-wide bandwidth applications such as car key fobs at this year's CES, the need for higher frequencies and wider bandwidth signal creation can easily be met with this type of architecture. But it is worth considering the other types of generators, because each has a benefit and trade-off. For high dynamic range with precise control of the peak to power ratio, as we learned earlier, by far an analog signal generator is the best solution. However, in the past this has been cost and size prohibitive, because only recently have multi-channel signal generators such as the Tabor Lucid LS1291, which is shown here at the top, has multiple synthesis blocks sharing a common reference, and this architecture contains up to 16 channels of phase coherent signals in a single unit. And you can, if you need more carriers, you can synchronize multiple units to create a very precise, advanced, high quality multi-tone measurement system, dial a peak to average ratio system essentially. Finally, we have vector signal generators. They offer wide power range, good dynamic range, as they ultimately utilize narrow bandwidth DACs, and then they have an analog IQ modulator. While the state of the art for this type of instrumentation allows for wide bandwidths and higher frequency ranges, a typical instrument used in communications or components for communication systems usually has a frequency limit of about 6 GHz and a modulation bandwidth of 160 MHz, making the current generation of these products not suitable for the evolution of wireless systems. Now, if we take a look at a commercial modem or an RF chipset that's available in the market today, it uses exactly the same principles of digital implemented complex IQ modulator to create the RF signal. And in the next section, Walt's going to look at how high peak to average ratio affects the architecture and cover some of the measurement techniques that can be used to understand it and mitigate it, ranging from clipping in the baseband system to brute force methods of just using a bigger PA with more headroom, more cost and more size, and everything in between. While distortion can be introduced in multiple points on this block diagram, he's really going to focus here on the power amplifier and help us understand the different measurement techniques to understand the peak to average ratio. Walt, over to you.
Thank you, Mark. My name is Walt Strickler. I'm the General Manager at Boonton Electronics. Thank you for joining our webinar today. To recap, Mark has shown as the number of tones increases in a waveform, the peak to average power ratio, also called Crest factor, will increase as well. You can see how the 4 tones in this example can add in the sum signal to create a significant peak in the overall power. As the number of tones grow, as in an OFDM signal, the Crest factor continues to increase. To put things in perspective, a 5-component carrier LTE-A signal may have 6,000 effective subcarriers or tones, and a 5G new radio signal may have as many as 3,300. So why is the magnitude of Crest factor so important? To answer this question, let's consider the impact on a communication signal. It's no secret that there is an exponential growth in the demand for mobile data. To address this demand, engineers are employing technologies that support high-speed data transmission, mobility, and efficient use of available spectrum and network resources. One of the staples across many communication systems is the incorporation of OFDM, which has advantages in these areas. However, to preserve signal fidelity and to achieve the desired signal data rates, components within a communication chain, such as an amplifier, must behave very linearly. While linear amplifier operation is very important, there are reasons you may want to tolerate some amount of nonlinearity. In this plot, we are showing input power applied to the amplifier and output power of the amplifier. As you see here, as the input power is increased, the output power is increased by the same amount. Where this occurs is the linear region of the amplifier. Ideally, the amplifier would operate linearly over its entire dynamic range. Unfortunately, amplifiers are not ideal, and the output power increase slows relative to the change in input power, until at some point the output power doesn't change in spite of an increase in input power. At that point, the amplifier is in saturation. Amplifiers typically operate most efficiently near saturation. Consequently, amplifier manufacturers often specify an amplifier's 1 dB compression point, where the output signal is 1 dB lower than the ideal linear response. System designers must then make trade-off between linearity and efficiency. The relative importance of the two attributes depends on the application. For example, in a satellite-based application, efficiency may be more important as there's limited power available on the satellite. In terrestrial wireless communications, the relative importance may be more equal. Communication systems, such as those based on 5G standards, utilize wide-band modulation schemes with significant linearity requirements. In addition, because of the amount of base stations needed to support the systems, it requires acute attention to power efficiency to manage operating expenses. Depending on the application, some input backoff is selected to optimize the linearity and efficiency trade-off. These measurements are often made on the average power of the signal applied to the amplifier. However, this doesn't tell the whole story. With an OFDM signal, the peak power may often be significantly higher, on the order of 10 dB, as Mark showed you earlier. So when the peak power is considered, the amplifier may go into saturation much sooner, and an additional backoff may be required. When an amplifier behaves non-linearly, it will distort the signal, which creates many negative effects. One of those is spectral regrowth. As you can see here, when the signal input backoff is 8 dB, the signal spectrum shoulders are fairly low. However, with less backoff, you can see those shoulders increase in magnitude. To try and reduce peak to average power ratio, many techniques can be used. You can see a few of those techniques here. Since many amplifiers are used in systems with modulated signals, a simple input versus output power curve is not sufficient to describe the amplifier's linearity. To estimate the response of the amplifier with multiple tones, the most common tool for assessing an amplifier's linearity is to inject the amplifier with two equal amplitude tones at either the outer edges of the amplifier frequency range or spaced by the modulation bandwidth of the signal with which it will be used. The output of the amplifier is measured with the spectrum analyzer. As the amplifier becomes nonlinear, it will produce harmonics of the two tones, as well as demonstrate a frequency mixing effect. The result will be intermodulation, and additional signals will be present as shown here. Good filtering can take care of most of the intermodulation products. However, the third-order products, highlighted in blue, are close to the fundamental signals and may be difficult to filter out. The products that cannot be filtered out cause intermodulation distortion. In simple terms, the result is a degradation in the output signal's signal-to-noise ratio. In radar systems, this can lower the sensitivity of the radar. In communication systems, it can increase the bit error rate and reduce the data throughput. To provide a single value to describe the intermodulation distortion, amplifier manufacturers specify an amplifier's third-order intercept. We start with the input versus output plot we used previously. To derive the third-order intercept, we select a specific power level for the two tones, and then we measure the third-order products. Then we draw an ideal amplifier response. You can see those here. And you'll note that the amplitude of the third-order products increases at a rate of 3 to 1 relative to the fundamental signals. The point at which the ideal responses intercept is the third-order intercept point, also called IP3. If the third-order products were lower, the third-order curve would shift to the right. This would move to the right. And the intercept point would be much higher. Therefore, the higher the third-order intercept, the greater the linearity of the amplifier. As a result, third-order intercept is a figure of merit for amplifier linearity. For example, this is the information provided on a recently released 5G front-end module by Qorvo. Under the key features, you'll note that they specify third-order intercept of the receive portion of the module, as well as the amplitude of the tones used for the calculation. An alternative approach for determining amplifier linearity utilizes crest factor measurements. To measure crest factor, we provide the amplifier with a modulated signal. Then we measure both the input and output signals with peak power sensors. Shown here are the crest factor measurements of the signal applied to an amplifier, that's this one, and of the output of the amplifier, that's the output of the amplifier. You can see that the magnitudes are essentially the same, indicating that the amplifier is operating in its linear region. Since this tool depends on making high-quality RF power measurements, it's worthwhile to take a few minutes to review a basic requirement of accurate peak power measurements. The ability of a diode sensor to accurately capture the envelope power or peak power depends on whether it can respond as fast or faster than the resultant amplitude change of the modulation. So let's look here, we have a pulse signal with modulation. So the sensor needs to be able to respond as fast as this rising edge of the pulsed signal, as well as be able to respond to the fast changes in the modulation. A common measure to use to determine the ability of a sensor to respond fast enough is video bandwidth. Peak sensors use a low impedance load across smoothing capacitors to discharge them very quickly when the RF amplitude drops. This, in combination with a very small smoothing capacitance, permits the peak power sensors to achieve rise times in the nanosecond range and corresponding video bandwidths of 10 megahertz. A rule of thumb relationship between rise time and video bandwidth is approximately equal to 0.35 divided by the rise time of the detection circuit. Measuring a pulse signal is the easiest way to visualize the effect of insufficient video bandwidth on power measurement accuracy. So when bandwidth limiting occurs, the measurement instrument cannot keep up with the changes in the signal being measured. So in this example, the sensor circuit response cannot change as fast as the pulse rising edge. It never reaches the actual peak of the pulse signal, and then is slower to fall off than the pulse. The same errors can occur during the fast peaks and dips of a modern wideband communication signal. In essence, the peaks will be rounded off, similar to the effects of a low-pass filter. So not only is the envelope or peak power wrong, the average power of the pulse will be incorrect as well. So it's important the sensors you use for your crest factor measurements have the appropriate video bandwidth. So here are the crest factor measurements shown earlier with the amplifier operating in its linear range. So as the amplifier is presented with higher input power, it becomes nonlinear, and the output crest factor decreases, which you can see in this measurement. So you can see, first of all, the output crest factor is much lower now than the input, and you can actually visually see the clipping that's occurring on the peaks. A crest factor measurement provides a single data point, just the maximum crest factor. Looking at a complementary cumulative distribution function provides even more information. A CCDF curve shows the amount of time a signal spends above the average power level. Or equivalently, the CCDF curve displays the probability that a particular crest factor will occur. So if we look at the plot here, this is the relative power above the average. This is the probability of occurrence. So we may want to say, how often does an 8 dB crest factor occur? So we follow the plot up, and we see that for 99.9% of the time, the crest factor of this waveform is 8 dB or less. So in the plot, the CCDF curves are provided for the input channel in yellow and for the output of the amplifier in blue, with an average power input into the amplifier of minus 11.9 dBm. Depending on the application, the probability of interest will need to be identified. So a common probability is 0.01%. So the marker on the curve shows the crest factor of the input and output signals for 0.01% of the time. The information for various points is also provided on the table on the left. From the curves, we can see that the crest factor for the input and output signals are virtually the same, and the amplifier is acting linearly for more than 99.9% of the time. So as the power presented to the amplifier is increased, so we've moved up now to -7 dBm, at some point it will begin to behave non-linearly and go into compression. And the output signal, CCDF, will start moving to the left. You see that here, indicating a decreasing crest factor. So looking again at the 0.01% probability of occurrence, we see the input signal crest factor remains the same, but the output signal crest factor has decreased significantly. In particular, the output crest factor has been reduced by roughly 2 dB. So as you can see from the examples we covered, crest factor and CCDF measurements are excellent tools to help you optimize the peak to average power ratio for wireless systems. Moreover, when used with a wideband signal stimulus, such as the Tabor arbitrary waveform generator Mark described, the crest factor approach has some significant advantages over IP3 for assessing amplifier linearity. Since we are using a wideband signal similar to the signal with which the amplifier will be used, the linearity assessment will be much more representative of actual amplifier performance when used in its intended application. The crest factor approach utilizes low-cost, wideband USB peak power sensors rather than a spectrum analyzer. As you know, spectrum analyzers can be multiples of the price of a USB sensor. Spectrum analyzers can be complex to configure and are ripe for user error. And the uncertainty for a power sensor measurement is usually in terms of tenths of a dB, while spectrum analyzers are typically in the 1 to 2 dB range. Companies throughout the industry are discovering the advantages of the crest factor approach. And Power RF Systems states in their technical reference material that using CCDF as a method for measuring the 1 and 3 dB compression points surpasses other methods as the means to analyze amplifier compression. With the Boonton Power Analyzer software, which is free to download, you can see the data as a CCDF chart and/or a CCDF plot, as well as see the actual measurement traces. In addition, the Boonton real-time peak US power sensors cover the 5G frequency ranges, have up to 195 megahertz of video bandwidth, which is more than adequate to measure the 5G 100 megahertz channels and Wi-Fi channels of 80 megahertz and 160 megahertz. They have a reading rate of 100,000 readings per second for fast results, and effectively sample at 10 gigasamples per second to ensure nothing's missed, even intermittent glitches or dropouts. So now I'm going to demonstrate some live crest factor measurements to show you just how simple it is. To conduct the demo, I will be using the Tabor Proteus arbitrary waveform generator with Wave Design Studio software to generate modulated signals, and the Boonton RTP 5006 peak power sensor and Boonton Power Analyzer software to make crest factor or peak to average power measurements and plot corresponding CCDFs. With this setup, you're able to evaluate different techniques to optimize peak to average power ratio for various wireless systems. Okay, now for a more interesting portion of the presentation where we're doing our live demo. I've had to exit out of presentation mode so I can switch between programs now. So this is Tabor's Wave Design Studio software. So I have preloaded 3 different waveforms, which were created with MATLAB. I have a 64-tone signal with random phase on each tone. I have an 802.11ax signal with an 80 megahertz channel utilizing OFDM with 16 QAM modulation. And then I have a second 802.11ax signal, this time with a 160 megahertz wide channel, again utilizing OFDM, this time with 1024 QAM modulation. So as I flip through these signals are probably not very recognizable in this representation. So I took some spectrum analyzer measurements, which are likely to be a little bit more familiar. So here's our 64 tones with random phase. Our 802.11ax signal, you can see it's 80 megahertz wide. And then our second 802.11ax signal, this time 160 megahertz wide. So using the Wave Design Studio software, I can use the Scenario Composer to download the signals to the Proteus Arbitrary Waveform Generator that Mark discussed earlier. And then I can simply select from the segment, whichever segment I want to play, and it instantly is transmitted. So let's start with the 64-tone signal. So we'll switch to the powerful Boonton Power Analyzer software to analyze this signal. So the 64-tone signal is being continuously transmitted. Since it is a continuous signal, the trace view is not very interesting, so we'll switch to meter mode. And you can see the average of the signal is roughly minus 13 dB, and the max is minus 6.4 dB, so the crest factor is roughly 6.5 dB. However, as we discussed, this is a single value and doesn't give the whole story. So using the statistical measurement features of the Boonton Power Analyzer, we can see how often that crest factor occurs. So as I mentioned, this is crest factor 6.6 dB, that's the max. You can see that's the max here. But if we look at the CCDF plot, we can see that for 10% of the time, the crest factor is roughly 4 dB or less. And even for 99.9% of the time, the crest factor is 6.25 dB or less. Because there are only 64 tones, it can require a significant amount of time for the rarer combinations to occur. And therefore, the curve falls off pretty quickly beyond that. So I'm going to put this in memory as a reference point for our next signal. Okay, so go back to our WDS, our Wave Design Studio, and this time we'll select our 802.11ax signal. Again, it's 80 megahertz wide. It contains 996 tones. So going back to Boonton Power Analyzer, let me turn off this memory so you can see our waveform a little more clearly. This is an 802.11 signal, so it's being bursted. So now we need to trigger. Turn the triggering on. You can see we've triggered on the rising edge. We have a very stable waveform. This is the average power. This is the peak power. And with our markers, we can select which portion of the waveform we want to make our measurements. So right now I'm selecting the whole waveform. You could potentially just look at the preamble and training sequence, or conversely, we could disclude that. But let's include it all for our particular measurements here. So go back to our CCDF plot. And we set it for this particular waveform. Now let's look at our stored signal. So a couple of things that you will observe right away. The first thing you'll notice is that the crest factor is much larger. So you can see the peak to average ratio now is maximum is 10.7 dB. And that's because there's more tones to combine together. Remember, there's 996, and we've added 16 QAM modulation. And the second thing to notice is that with more tones, there's more opportunities for these rare occurrences to occur. And you can see the rest of the CCDF plot is filled out. So let's put this one in memory now. And let's look at the remaining 802.11ax signal. So again, this is 160 megahertz wide channel. Now it's 1,992 tones. So going back to our Boonton power analyzer, again, turn off the memory so you can see what's going on. This signal looks very similar to the previous one. Again, we can pick whichever portion of the waveform we want. So now we'll go to our CCDF signal. And reset it for this new waveform. And then turn on the memory. So you can see here that with the wider channel bandwidth, now 160 megahertz wide, and the 1024 QAM, the crest factor has again moved to the right, again increased. But it does have a similar shape this time. So one thing I'd like to point out again is that the Boonton RTP 5006 I used for these measurements is the only sensor on the market with sufficient video bandwidth, 195 megahertz, to make these measurements. The majority of competitive products top out at only 30 megahertz of video bandwidth. So with these tools, you can measure peak to average power ratio on various signals and determine which is the best for your application. Or you can also look at various peak to average power ratio reduction techniques and use these tools to determine which is most effective. So now let's wrap up and open up the floor for questions.
Walt and Mark, please wrap up for us, and we'll then go into the Q&A session.
Thanks. So the changing nature of communication signals. So in the first part of the presentation, I talked about two tones, and then Walt also talks about two tones and how they are good. It can show your intermodulation performance. You get some peak to average ratio as well, but really to fully understand how a modern communication system like wireless LAN, LTE, 5G, ultra wide bandwidth works, you need to either use a lot of tones and use a dial, a peak to average ratio measurement, or use a real signal. So we explored the differences in bandwidth, subcarriers, and modulation techniques in the first part. And then we also took a look at signal generation techniques, because there's many ways you can do it. You can either use an analog signal generator, or you can use an arbitrary waveform generator, or you could use a vector signal generator. Well,
so we covered the importance of peak to average power ratio, in particular with the example of the amplifier linearity assessment. We also said that we need to make sure that the video bandwidth of your peak power sensor is sufficient. And with the wide bandwidth channels, for example, an LTE with 100 megahertz or Wi-Fi with 80 and 160 megahertz channels, that really limits what you have available to utilize. We showed that peak to average power ratio is a very good tool for linearity assessment, in fact, better than the traditional IP3 third order intercept. And we also saw that although peak to average power ratio gives you good information, you can get some additional insights from the CCDF plot. And then hopefully you were able to see that in the live demonstrations. I think we're ready for questions.
Yeah, we'll move on to the Q&A. Thanks, Mark and Walt. Great presentation, and like the live demo. So first question, and I think this is for Mark. Can you comment on the amplitude range of the arbitrary waveform generator?
Yeah, the waveform generator has 14 bits of effective range. So it's a rule of thumb is 6 dBs per bit, and then you add like 1.75 dBs to that. So I'd have to work it out in my head, but I think it's around 80 dBs of range, and then we have a variable voltage output stage, so we can adjust the peak-to-peak output voltage up to about 1.2 volts.
Great. And next question for you too is, you mentioned some different phase distributions when using multi-tone signals. Are there more than ones that are not mentioned?
Yeah. No, I talked about four. Our expert Joanne's going to take this one.
I can take this one. Thank you, Mark. This is Joan Mercader. I am an application engineer at Tabor Electronics. Yeah, there are so many distributions for multi-tone signals that are basically designed for reduction of the peak-to-average power ratio or to control it, so you can get the right peak-to-average power ratio or the Crest factor for a given experiment. And most of them are very similar to the Shapiro-Rabin sequence we have used it in the demonstration in the seminar, but they are also even better than that, like the parabolic distribution or Newman distribution that provides a very good peak-to-average power ratio, which is constant for any number of carriers. So yes, there are many other possible multi-tone signals that are suitable for testing and with very good or controllable peak-to-average power ratios. Okay.
Great. Next question I think is for Walt. We realize IP3 is no longer a sufficient way to determine true amplifier linearity and now perform EVM measurements. How does the Crest factor linearity assessment compare?
So that's a good question. I actually think that EVM and Crest factor linearity assessment are very complementary. So EVM can provide a very in-depth analysis of nonlinearity, of the nonlinearities that can affect the signal quality. And this is great for the initial design and associated verification. In fact, through this analysis, engineers can determine what Crest factor reduction can be tolerated and at what rate of occurrence. Then, rather than using a VSA in production test, companies can utilize Crest factor linearity assessment. So as you know, VSAs are very expensive, they're complex to use, and much slower than a simple, low-cost, ultra-fast USB peak power sensor like the RTP 5006. So I think, again, they work very well, very nicely together, and the Crest factor tool is really what you want to look at for production test.
Got you. And so next question for you. You mentioned the average power measurements don't tell the whole story. Can you explain a little more about that?
Yeah, I'd be happy to. In fact, let me try with a real-world example. So we were working with a company integrating a Wi-Fi chipset into one of their devices, and they were having trouble achieving the data throughput that they expected. So as part of their troubleshooting activities, they were measuring the average power out of the chipset. And the measured level was below the chipset saturation level, and the gain was staying relatively stable within a couple tenths of a dB, so they were satisfied that the power level was not the issue. So they went on to dig into their modem and codec performance, which is very complicated, time-consuming. So in parallel, we suggested they examine the signal Crest factor. So it turns out that looking at the Crest factor, which was normally around 11 dB, at the power level they were transmitting, they were seeing compression of more than 1.5 dB. So they reduced the input signal, and poof, the data rate jumped right back up to what it was expected. So that gives you a good example of why looking at Crest factor and peak power is more important than looking at just the average power.
Okay, great. Next question. What technique is used to do Crest factor reduction?
Okay, I'll take that one. There's actually quite a few techniques and several academic papers on the subject. In my presentation, roughly around slide 20, I give you a list of about 10 to 12 different techniques. Clipping is probably the most frequently used technique.
Yeah, just to complement that, this is Joan Mercader again from Tabor. Those compression techniques can be easily implemented in software, and then apply it to real devices under test using AWGs, for instance. So that's one of the nice things about AWGs. They can generate perfect signals, but they can also generate distorted signals in such a way you can perform very well-controlled tests in any receiver.
Great. And next question, what would be a good peak to average power ratio for typical applications like 5G versus maybe a man-pack radio? And then, what is kind of a typical back-off that people use?
So for 5G signals, the Crest factor is typically between 12 and 15 dB, depending on what, how wide the channel is, what types of modulations are being used on each of the tones within the OFDM signal. So it can vary. And then what was the second part of that one, Pat? Sorry.
And then, so people usually end up backing off the amplifier. What's a typical back off in different applications?
So that one I can't answer because, as I was talking about earlier, there's a trade-off between linearity and efficiency. And you have to understand what the tolerance of nonlinearity that your device can accept and still maintain, if it's communication signal, maintain the data throughput. But then you have to balance that with how efficiently do you need the amplifier to operate to meet your OpEx expense goals. So there's no one answer. It really depends on the specific application.
Yeah, this is a complex one. It also depends on the signal characteristic and what back. You could types of filtering.
I think you're dropping out there, Mark. If you could start over on that answer.
I said it. If I hope you can hear me now. It depends on the signal itself that you wish to generate as well. There's multiple, and Walt alluded to them in his part, and I talked about it in my part. It depends. You can also reduce the peak to average ratio at the baseband level by using the technique called clipping, and there's a various bunches of different types of filtering that you can do to try and bring it down so you get a little more headroom at the amplifier itself as well. But in general, the more carriers you have, the more complex modulation you have, the higher peak to average ratio you're going to have.
Yeah, just to complement, LTE is a very good example. In LTE, you use a different modulation in the downlink and the uplink. In the uplink, it is optimized for a low P Crest factor, so you get a better performance regarding power consumption in a typically battery-powered device. So in this case, it's the peak to average power ratio, which is really defining the modulation scheme that you are using.
Great. I think we've ran out of time here, so wanted to thank Mark and Walt and everybody who jumped in on the Q&A session for this great webinar, and thank Tabor Electronics and Wireless Telecom Group for sponsoring it. You can find out more about their products mentioned here and more on their website. Please note this webinar has been recorded, so it'll be available to watch in a few hours from now. You'll find it in the events section of the MicroWave Journal website. If your colleagues would benefit from watching it, please let them know. And we thank everybody for joining us today.
Thank you.
Thank you.